save on the computer. I've given up on saving to cloud. It just never seems to work quite right. I think we're recording.
Yeah, it's recording.
Good. Okay, don't show a message again. I've got Zoom stuff everywhere here.
Hi, Joss.
Hi, Tor. Tor, could you just send a message out?
Let's give us just until 10:15 European time for people to work out the problems and hope that as many as possible can join, and then we'll start the meeting.
Yeah. I'll send an email to our group, Joss.
Thank you.
Hey, hi. Hi, Matthias.
Hi there.
Yeah.
So hi Feng, I almost passed that test, intelligence test of I got Densent installed. Used Chinese transcribing to try to figure out.
This time, very careful. Yeah.
Yeah. I got so far, then failed.
All right, Joss. I think you got the email too because you're on the list.
Thank you. I'll just turn my email off now. Stop the pinging noise.
Yeah. Enough. Yeah, I was having trouble with this system from the start. I actually tried it this afternoon and it wasn't working. And I thought maybe it's because the session hadn't started yet.
Yeah.
But I tried everything and it didn't work. I don't know why.
Yeah.
I think it's a progressing technical separation between different spheres of influence. Let's phrase it that way.
Yeah, it wanted it. I got past one security setting which said, now you now need to type in a Hong Kong phone number. Oh dear. Yeah, I couldn't see how to get past that. I'll get things ready. So we've got a chat window, hi Feng, so if you need to message people as well, get that going. All right. I'll go into share mode.
Yeah.
Good.
Fantastic.
Very nice. There we go.
And please, everyone who's not speaking, don't forget to switch off the mic. All right, I think we should start. I use this meeting as a warm welcome as a president of the IU Commission H1 Local Universe. We, during Corona time, instated an online seminar series, in particular to give the young upcoming talent an opportunity to present their work to a larger audience. And nowadays, Corona is a matter of the past, I hope so. But we thought it still may be good to, continue that series. So we take today's event as an opportunity to restart the seminar series. It will also be recorded on video and audio, and then transformed in a YouTube video format and will be uploaded to our YouTube website. So everyone who missed today's meeting will have the opportunity to look at or to see the presentation at a later stage. And I'm particularly pleased for our startup session to have someone who's not really a young career scientist anymore. So he stays young forever. Jos Bland-Hawthorn of the University of Sydney. Jos is a very well accomplished person in galaxy studies and in particular galactic archaeology. I think he's even one of the word framer of the word galactic archaeology based on his famous review with Ken Freeman of 2004, clearly seminal, 2002, sorry, clearly seminal paper in our field, and a more recent review on the Milky Way together with Ortwin Gerhardt in 2016. He also is quite known for his work on gas dynamics in galaxies and also for technology development, in particular in the field of astrophotonics, so using state-of-the-art, newest photonic technologies for the field of astrophysics. And I think that's a much praise for the moment. We are here mainly for scientific talk, and I hand over to our chairman and secretary of the commission, Haifeng Wang. Or just maybe you just go ahead and start with your presentation.
Okay. Thank you very much. And thank you so much, Matthias. Thank you also for this new format. And I know these have happened before in different ways. It's great that we have this new opportunity to discuss the science in the local universe. There's so much going on. Just when you thought that we'd reached an important point and we could just sit back on our laurels, along comes James Webb and ALMA, and things have started afresh all over again. Like we don't really know as much as we thought we did. So these are very exciting times. And I just got a picture here of University of Sydney campus and a few names. This is work with Torsten. He's been a very important figure in all this work for the last sort of 8 or 9 years. Oscar Agertz, who's a very important collaborator of ours, who does work on simulations, and Christoph Federath, who is a superb theorist on the gas dynamics, and he sort of keeps us honest, as it were. And what I'm showing you here is a picture from a cosmological simulation. It's been touched up with clever rendering techniques of what a Milky Way analog might look like, going from high redshift down to low redshift. And in fact, this is attached to a movie that looks like, let's see if I can get past the zoom, just remove the zoom window for a moment. And here's a movie that rendering was taken from by Oscar and his team, Francois Renaud and others. And it shows you the gas component. When you start to see blobs of red appear, this is the cold molecular gas. The rest of it is sort of a diffuse gas and maybe even warm H1. And what you're seeing here is the evolution of the baryonic component at the sort of precursor Milky Way phase. And by about a redshift of 3.5, you start to get a cold disk in rotation. I think you'll see it about now-ish. And this is particularly nice work because they're trying to generate Milky Way analogs, as it were, in these simulations. And they were able to get this to occur at about a redshift of 3. You can see it sort of coming in here, edge on. Whereas a lot of the other simulations, disks were forming by a redshift of 2 or 1. So what's extraordinary is that today we observe disks up to even a redshift of 9, if ALMA is to be believed. And so these simulations really have been sort of outdone by the real universe. Disks got going much earlier than even our best simulations have been able to produce. People have begun to touch up their simulations. They use more massive precursors. That helps a bit. And they also do the rendering of the simulations at higher resolution. And again, that helps a bit as well, like shock capturing and so forth. But still, they're not getting disks much earlier than about a redshift of 3.5, 4, or 4.5. So how on earth disks get going by a redshift of 9 is something that we would like to understand. And if I take this down to a redshift of almost 0, you can see that Oscar does a very good job of producing a cold molecular disk with a diameter of about 20 kiloparsecs. So it really is a nice sort of narrative as to how Milky Way-like galaxies form. So the work I'm going to be talking about is over the last 2 or 3 years. It's been published with a sort of focus on this paper, which was put on AstroPH 4 months ago, turbulent gas-rich disks at high redshift, origin of thick stellar disks through 3D baryon sloshing. And this has a rather large team Misha, Hayward, Paolo, Dimateo, Tim Betting, Takafumi, Emily, Melissa, and Ken. So we're sort of a team that brings together studies of old stars, studies of new stars, theory, simulations, and the high redshift ALMA work. In particular, Takafumi has been a focus of his beautiful work on early disks. Okay, so this is the sort of the background of the work. So let me just give you a bit of context now. If you go back to about 2014, there were reviews using HST imaging and looking at disks versus spheroids versus peculiars. And the story there, at least, was that the spheroids were falling by a redshift of 2. Disks were in sort of the rather no, there were disks were the number counts were falling dramatically by about a redshift of 1, 1.5, down to 2, and peculiars made up the missing component. That story has changed since the advent of James Webb. There are several papers on this, Ferreira and Cartel-Tepe in particular. And Ferreira shows you that the spheroids, the disks in particular, dominate over the spheroids in sort of rest frame red bands and J bands and so forth. And the peculiars are actually on a decline. And that story appears that story appears to be true, even if you split them into low mass and high mass bins, like sort of baryonic masses below 10 to the 9.5 and above 10 to the 9.5, you still see these blue squares of the disk component, and you still see that these disks dominate over spheroids out to about a redshift of 5. So this is a very different story from what we were being told. I was told in graduate school 20, 30 odd years ago. We were told that spheroids formed by about a redshift of 4, they were heavily quenched, disks formed by a redshift of 2 or lower. But the story is very different, I think, I would say now, when you look at what James Webb's telling us. And to be fair to ALMA, ALMA's been saying something like this for even longer, sort of decade before James Webb, that there were these cold disks up to a very high redshift, even higher redshifts than 5. So what I've got here is a plot from the Cartel-Tepe paper showing you their survey sample, which gave you these results. And what you see here are essentially the Milky Way progenitors would be around 10 to the 9.5 plus or minus something at a redshift of 3 and 4. But of course, that baryonic mass would decline to even higher redshift. So what's extraordinary about these galaxies is that, yeah, sure, they're precursors to modern day disks, but the star formation rates were much higher. And we think the gas mass fractions and the disk mass fractions, the disks were dominant over dark matter, over the scale radius of the disk, and the gas mass fractions were much higher than modern day. Modern day disks would be about 10% gas fraction, whereas what we're seeing here have much higher gas fractions. So we're obviously seeing a very interesting early phase of when disks were dominant, and disks were also very gas rich with very high levels of star formation, high rates of star formation. So the goal, in a sense, is to relate all of this to modern day galaxies, which is of course not very easy, because we can't trace one particular object all the way through cosmic time. What we see are samples at different redshifts, and we try to join the dots with some kind of a narrative. In modern day galaxies, we do see an old component. This is a beautiful reconstruction. It's sort of pointillism. Every dot you see there it's not an image. It's a star with fit parameters, and it's been essentially reconstructed from stellar photometry over hundreds of thousands of sources. And what you see there is an exponential disk, which is much like the Milky Way, but also this sort of faint diamond-shaped thicker disk, which extends to much more than twice the vertical scale height, and possibly even further in radius. And of course, a much larger radius, you see faint loopy structures, presumably from infalling satellites. So what we know about thick disks today, and there's not many thick disks which have been looked at chemically, I'll get to that in a moment, but the thick disk today, at least in the Milky Way, possibly in the M31, has enhanced alpha to iron abundances compared to the thin disk. Now, the thick disk to thin disk mass ratio can be 1 to 1 in some papers, can even be 1 to 3 or 1 to 5, depending on how the separation has been done. But this high alpha component is a significant component, and I think uniformly agreed to be very, very old compared to the low alpha to iron component. This was first realized, not chemically, but the fact there was a distinct thick disk and a thin disk was first realized by Gilmore and Reed in 1983. As to what causes these old alpha-enriched thick disks, there are loads of papers going over decades, really. And there's interpretations in terms of accretion of satellites, heating of disks from mergers, or even gas-rich early mergers producing some kind of violent phase, radial migration from some sort of massive bulge, bimodal star formation, and also this idea of in situ star formation in a turbulent gas-rich early disk. This last one comes up in my story, and I don't think this is a correct interpretation of where these thick disks come from. So what we're looking at now is, in fact, simulations of gas-rich disks inspired by the Wintergarten simulations. We sort of take one of these redshift 3 galaxies, we sort of idealize it in terms of a control galaxy simulation and sort of evolve it forwards. But what we do is concentrate on disks with very high gas fraction, which has been difficult to achieve in a controlled environment up until now. Is it the case that all galaxies have more than one distinct disk? I think the short answer is no. There are these super thin disks, which if you look at these papers, they tell you that they have modeled it in terms of sort of a set-squared vertical disk, and only one disk is required, and they're sort of overlapped, that they've sort of done a mirror symmetry subtraction as well, above and below. And as far as they can tell, there's no sort of residual component left over. So I think it's fair to say though that these single disk components with no detectable thick disk are relatively rare. I don't know what the numbers are, but whenever I see these papers, they talk about these as being difficult to find. But there are disks that have single component exponential disks out there, which is kind of interesting that sometimes you get these very fragile, cold, thin disks without a secondary disk, which is clearly has to be in the narrative somehow. So modern day surveys have really sort of begun to capitalize on this idea of old thick disks versus younger thin disks. This is one particular program, the GECKO survey, led by Jesse van der Sande, University of New South Wales. They have 30 plus disks, which are all within a factor of 2 of the Milky Way mass. And there's now MUSE observations of all of these disks, and they're doing sort of chemical differentiation between the thick and the thin disk. And there's clearly alpha-rich disks and alpha-poor disks, sometimes more alpha-rich than alpha-poor and vice versa. So there's clearly a complicated story going on here. The big papers have only begun to appear recently. Mary Martig and colleagues have been putting out some nice work. What's particularly interesting about this survey is that they've got ALMA disks. They've got ALMA observations for, I believe, all of these now. So you've got not just the stellar content, you've got also the gas content, at least the gas content today. So this is going to be a very interesting survey to see what we can pick out in terms of alpha-rich, alpha-poor bifurcation, or if it's always one or other or both, depending on the chemical history depending on the evolutionary history of the galaxy. Another survey which I wanted to point out is Takefumi's survey with Emily. They're using the James Webb and trying to do disk decompositions from about a redshift of 1.5 down to the present time. And they've got a paper out relatively recently. Ken and I are co-authors on this work. And there's some very interesting insights that come out of that. Again, you don't have chemistry at the moment. You don't have alpha to ion sort of separation, but you do have the kind of work that has been done before in terms of red and blue disk separation to look for these sort of old red disks. Anyway, this is some very nice work you might want to catch up with by Takafumi. So what's particularly interesting to me is the following, and in a sense, it's something that Torsten and I had talked about going even before James Webb was launched. We were well aware of what ALMA was showing, and others had talked about in terms of early universe disks being gas-rich. And I would say that has to be that part of the story that all disks that emerge from that epoch have gone through a gas-rich phase. So the question then is, what can we learn about that gas-rich phase, and what are the sort of signatures that survive to the present time that we can go after? What's particularly interesting was this paper, one of the first papers that really hit home with me that James Webb had a lot to say. These are 4-micron images from Guo et al. And every one of these you would say looked like modern day disks, spiral arms and bars. And you could find modern day counterparts, redshift is 0, that looked much like all of these objects, which I think was a surprise that the bars and spiral arms were seen at such an early epoch, sort of what you might call mature disks with these sort of delicate features. Other observations along these lines, there's a beautiful paper by Huang et al. Came out recently in Science, where you've got these sort of bar-like spiral galaxies. And what's particularly interesting is that these bar-like structures have gas all along the bar, and in some cases all along the spiral arms. So you've got sort of gas bars quite literally, and this seems to be a feature of these ALMA observations. You see bars streaming, and you look where the mass is being residing, and it's in the gas, and the gas makes the bar. It's quite extraordinary. This same feature is seen in the C1 1 to 0 transition as well. It's been seen in other transitions, in addition to C1, C2, and CO. There's also work by Takafumi and colleagues going up to even higher redshift. I think there's at least half a dozen disks now with bars and spiral arms seen at redshift of 4. These have velocity fields from the C+ line and even velocity dispersion maps. So it's quite extraordinary what's going on in terms of bar-like, bar bulge disk-like properties, spiral line-like properties of early disks. Okay, so what is particularly extraordinary to me is that I was always led to believe that these were relatively delicate and organized dynamical features that require certain disk conditions to be true, like cold disks in particular, and of course, driven by stars rather than gas. But when you look at these galaxies, this is the 6 from the Guo et al. Paper, they have very high star formation rates, and they all have very high gas fractions. So when you look at Linda's paper, she shows you for her sample of galaxies, this is a redshift of 0 up to redshift of about 9, that the molecular gas fraction compared to the total gas fraction, these are disk objects, is increasing up towards high gas fraction, at least 40, 50% in gas fraction. So this makes the point that these early disks, whatever they are, or how they form, they went through a very, very gas-rich phase in terms of their settling. And then, I mean, there may have been pre-existing stars that got in there from some other process, but at some point in their past, maybe a redshift of 1 to 5, 1 to 6, in that sort of phase, epoch, there was a phase through which the disks went through a very gas-rich phase. And that's what we would like to understand from controlled simulations. So what we're doing is revisiting this era with this code being developed by Torsten, myself, Oscar, and Christoph, which is to understand how disks evolve when you have a very high fraction of gas. And we would argue that very little is known about this, at high resolution at least, in terms of what gas does to you. So we're discovering remarkable properties. I'll show you a few of these now. And in summary, at low gas fraction, stars tell gas how to move, and the reverse is true at high gas fraction. In other words, when the gas fraction gets above about 30%, gas tells stars how to move. And this is something that you will not get from Binney and Tremaine. Binney and Tremaine is very much about cold disks, really about 2D disks, and the dynamics of 2D disks with essentially as elastic, as particles which are incompressible, basically stars. Whereas what we need to do, I think, now is update our knowledge about dynamics of disks, evolution, formation, and evolution in terms of disks which go through a gas-rich phase. There's 2 definitions which I just put up very quickly. These are totally standard. F disk is the extent to which the disk dominates over the dark matter, and that's measured in terms of the scale radius, 2.2 R disk. This is where the rotation curve is flattened off, sort of half light radius or half mass radius or something. And essentially that's the disk rotation speed over the total rotation speed squared at that radius. And F gas is just a proportion of that disk out to that scale radius in terms of gas. So F gas of 0 would be, it's all in the stars, a pre-existing stellar disk. F gas of 100%, but all the disk mass would be in gas. These are just bog standard definitions. So here's a quick summary of what these simulations look like. This is from Torsten's recent paper, Nexus Framework for Control Simulations of Idealized Galaxies. And there are 2 basic classes at the present time. This is a CDM with a hot halo, which does not cool, and a stellar and a cold gas disk. This would be 0% gas, 10, 20% gas, 40, 60, 80, and 100% gas. And the other class of models allows for cooling in a hot halo. So this is more like the Mao White approach, where you allow for disks to build up from a cooling hot halo. And that's something which is being explored in some detail now by Torsten. So these models have taken us a long way already, and we feel we're beginning to see some really important issues, or understand some important issues. But the one thing that we have not done so far is to install MHD. And we've done MHD work in the past, but we haven't got it working within the context of a galaxy framework yet. MHD will be important. For one thing, it carries cosmic rays up into the CGM and heats the halo which you're wanting to cool and drizzle gas onto the disk, of course. And it also affects the cloud spectrum, as far as we know, which affects the star formation rate across the disk. So in a sense, we think this is as far as you would want to go in terms of hydro for now, at least. But what we are missing is the all-important MHD phase, which we're well aware of, and I think will certainly affect how disks evolve over billions of years. And we know, I should be careful actually, we know that's true from Christoph Federer's work. He does these turbulent disk simulations, 10,000 by 10,000 by 10,000 over a kiloparsec volume, and he looks at hydro versus MHD simulations of turbulence cascading over enormous dynamical range. So we know that from his work that MHD is important. Okay, so let me just give you an idea of what these simulations look like. The middle is the gas evolution seen from above, from the side, XZ and YZ. This is XY, XZ and YZ. The bottom is showing you the new stars forming in the same projections, and the top is the pre-existing stars. This is a disk with pre-existing stars. So this is a disk mass fraction of 50%. So basically the baryons dominate over dark matter over the inner disk, much like the Milky Way and M31. So if I just run that now, you'll get a sense of how the gas couples with the halo. And in fact, the star formation generates metals. It also generates energy and momentum, and that gets injected into the surrounding gas, which is what keeps the gas turbulent and supported from collapsing to a billion black holes or something. I'm showing you here the lower resolution version of the simulations so that this would actually be rendered in a reasonable amount of time. Okay, so from work by Fench and Bourneau, one thing we do know is that when you get up to high gas fractions, even at relatively low resolution, the spectrum of clouds has a sort of power law appearance, and it looks at 10%. It looks pretty much like what you see in the Milky Way, and we don't have a plot as fancy as this one yet. But at 55% gas fraction, what you see here is the cloud spectrum is shifted to high mass clouds, and so Fench and others and Bourneau and colleagues, and before them Elmer-Green, have made this point that if you start to see very massive clouds in these early galaxies, that probably is a sort of a signature of a high gas fraction in these early disks. So I think there's pretty good evidence that these early, even quite apart from disks which have James Webb and ALMA as well, in combination. But I think there's pretty good evidence that these disks do in fact have very high gas fractions at early times. Okay, so some of the things that you can learn from these simulations. First of all, the no halo accretion. This is what the star formation rate looks like at different gas fractions as a function of radius and time. And what you see here is the star formation is sort of rather centralized, and it has this sort of radial gradient going all the way out. If you go to the halo accretion simulations, where you're supplying gas onto the disk, then you sustain higher levels of star formation across more of the disk in radius and in time. And what you do pick out here is just how stochastic it is. And that's an important part of our story. Stochastic star formation, which results in sort of momentum recoil, does real damage to the gas disk, and in turn does real damage to the stars. It basically pushes the whole disk around, starts to slosh in time, as I'll show you. Okay, so one of the things that we've been very attentive is to try to match some of the signatures that you see in the high resolution simulations by Christoph's team. So this is sort of alpha virial. This has been logged. This is the blue curves are the inner disk, the inner central region of the simulation, and the red curves are the outer disk region. And what these four properties are, these are the four properties which Federath and colleagues have identified as the most important in terms of the star formation rate and star formation efficiency across the disk. The first one is turbulent energy. This is the turbulent energy, 2 times the turbulent energy divided by the gravitational potential energy. And this basically, as this alpha rises up to some maximum, some threshold value, has an important multiplying effect on the star formation. Something else which was a bit of a surprise to me was the Mach number. As you get a higher and higher Mach number, you also encourage higher levels of star formation. But other important considerations are as follows. This B parameter tells you what the turbulence looks like. At B of about 0.3 versus B of 1. B of 1 it's sort of very compressive and it expands and contracts, sort of curl-free kind of gas motions, whereas this is like divergence-free. This is more like helical solenoidal gas motions. And what Christoph and colleagues have shown is you need a combination of those. You need somewhere between helical motions and compressive motions to maximize sort of the cloud formation and therefore star formation. And this is the normalized plots of star formation rate per unit freefall time. So if that's about a value of 0.1 down here somewhere, it means you've got 10% of the gas cloud being converted to stars. So in individual cloudlets, the star formation efficiency is rather high. The cloud overall, I mean, the overall molecular cloud, which is collapsing, may only have a few percent star formation efficiency, but individual cloudlets, which are collapsing out of that cloud, can have much higher star formation efficiency. So these are sort of things that we've actually managed to extract from our simulation. So I'm not saying we're doing as well, anything like as good as what Christoph is doing, but we are able to see the sorts of signatures that he sees at much higher resolution. So here are some of the early results, which are quite interesting. First of all is the formation of bars. So what we're finding is that the bar length, bar mass, and bar formation time scale inversely with the gas fraction. This is sort of a loose statement. It's sort of a rather a noisy process. But you can see here at 20%, 40%, 60%, 80%, and 100. Sorry, these are existing stars. Sorry, so there's no stars in this one. So this is the stars that form 20%, 40%, 60, 80, and 100%. And what you see here is that these young bars that form, the length gets smaller as the gas fraction increases. Something else that we see, and that's with no halo accretion. This is with halo accretion. You see the same story. But what's particularly interesting is at the very highest gas fractions, these gas bars, which are around for maybe 1 billion years, don't survive. They collapse to form bulges. So here's the galactic potential of one of those simulations. And you can see this nice bar in the galactic potential collapses to become spherical as a consequence of that. So if at high gas fraction, these gas bars don't sustain themselves, don't stay up. They sort of are unable to. If they're larger gas bars, they seem to survive longer. But the very high gas fractions, the gas bars are overwhelmed by other forces and then sort of collapse to something spherical. So this could be an interesting path to early bulge formation at these epochs. So that's just a very quick summary of and there's a much longer story about this in our 2024 paper. Okay, something else which cropped up, which I was particularly excited by, was this. We see these m equals 3 phases when you're at high gas fraction, where you have 3 spiral arms rather than 2 or 1. And what seems to be going on here is that these disks are sloshing around, and you've got this sort of m equals 1 in the gas, and they're triggering bars and spiral arms, and then m equals 1 and m equals 2 working together seems to trigger the m equals 3 effect, at least for a few rotation periods. Interestingly, this was something that was first discussed by ALMA long before these simulations came along. I raise that with you now because there's an m equals 3 spiral galaxy, which was first published in 2012 by Law and colleagues at a redshift of 2. But what's particularly interesting is a few weeks ago, this paper came out by Espejo, Salcedo and colleagues, where they were able to analyze. This is from, I think, is this the one from? No, it's not the one from Galaxy Zoo. Sorry, that's the one they connect to. Apologies. But there's a Galaxy Zoo paper that does this at lower redshift, and what they find is that m equals 2 dominate at a redshift of sort of, well, I suppose 0.8 to 2.5. But they find a remarkable fraction of m equals 3 spirals as well. This is much more than I thought, because it used to be said, of course, that the m equals 3 spirals in the local universe was only about 5 or 10%. Galaxy Zoo actually finds they're more like 20%, which is interesting. M equals 4 spirals are relatively rare. But what's particularly interesting is they find an excess of m equals 3 spirals in these high redshift James Webb images, which is kind of interesting if this really is a signature of a gas-rich disk, which is where the gas is being used up. All right. So my punchline, though, what I really want to get to is what's actually going on with these gas-rich disks. So let me show you the first one. This is a simulation seen from above and from the side. And these are movies that were made by Torsten. And what you're seeing here is where the baryon centroid is with respect to the total gravitational potential well. And now this is this is zero gas fraction, I think. Yeah, zero gas. So there's no gas in this one, just stars. And what you see here is that the baryon disk, this is just stars, there's no gas, starts to wobble around plus or minus 50 parsecs. Sorry, plus or minus, yeah, 50 parsecs, 0.05 kiloparsecs. And this effect has been seen for many years in simulations. People have long known that baryons within a dark matter potential, bit of a Poisson noise effect, start to wobble around. What we're seeing here in particular, which I'll get to a little bit later, is that this motion, which fills the plane in 2D, is a bit compressed in Z in 3D, I think for reasons we understand. Okay, so you can just remember that this baryon sloshing is over a small scale, 50 by 50 parsecs or so, or 100 by 100 parsecs in total. If you go to 40% gas fraction and look at what happens there, notice the scale now is much larger. This is 800 parsecs by 800 parsecs in both directions, and in Z, 800 parsecs by 800 parsecs as well. And what you see now is the baryons are moving around much more. You can see that there's sort of circularized motions and drifting motions. And in Z, you can see it's pretty bizarre how this thing is moving around. And this is to scale. This is what you see compared to the gas, the case with no gas. And you can see this is a much more dramatic effect at 40% than it is compared to no gas at all. So this is being driven by something about within the gas. And what it is momentum recoil. Star formation region goes off over here, injects momentum into the gas, star formation region goes over here, and this sets the whole disk swaying basically within the gravitational potential well. This is what happens at high gas fraction. Let me show you, let me skip a whole bunch of movies and show you the 100% case. This is the 100% case. And now the scale, no, it's not. Sorry, apologies. All right. This is the 100% case. So now the scale is much larger. This is 3.5 by 3.5 kiloparsecs on both axes. And this is 2 by 2 kiloparsecs, plus or minus 2 kiloparsecs in X and Z. And what you see here is the disk is basically pirouetting and moving around over much larger scales. And there's a circularizing effect, which I think is a consequence of dynamical friction, because this whole galaxy is moving within the gravitational potential well of the dark matter halo mostly. And this essentially is giving us sort of a circularizing motion. That's something that I've seen in Binney's work and also in Larry Widrow's work. And then you can see that at the end of the simulation, it goes into this sort of coasting phase. So this is now quite dramatic. If you put them all together now, let me just show you this one first. This is with the no gas accretion. And this is in X 20%, 40%, 60, 80, and 100% gas fraction. You can now see how the effect becomes amplified as the gas fraction increases. This is what you get when you have more gas dumping onto the disk because of the halo cooling. And now the sloshing motion is over a much larger range. Okay, let me just turn off the chat window. I thought I was being asked a question, sorry. Okay, so if you then plot that motion, it's essentially Brownian motion. If you plot what the centroid is doing in 3D, as far as we can tell, this effect is essentially isotropic. It doesn't pick out a particular direction. It really does depend on the lever arm of where the momentum recoil happens, I suppose, and just how the star formation region blows out. So what you see here is essentially the centroid is moving. This is in time from 0 to 2 billion years. You see it's rather this erratic behavior, and it's sort of trying to fill the box. So essentially what you've got is this galaxy which is sort of moving around in this sort of rather stochastic way inside of the dark matter halo. Sorry. So first of all, the compression that we saw in Z, in XZ by a factor of 2 compared to XY, is a consequence of the fact that the disk being dominant over dark matter means that the gravitational potential is squashed by about 70% in the vertical direction. And so the restoring force in this direction is stronger than the restoring force in this direction. And essentially, so I think all you're seeing there is that the disk is moving around and it's just reacting to the overall shape of the potential well. So there's nothing mysterious about that. In fact, you can do a better job of modeling this if you add another term, which is the dynamical friction term itself, Chandrasekhar friction as well. So you have basically allow this galaxy to oscillate in this way and also allow for the settling effect over billions of years caused by dynamical friction. So I think dynamically it all kind of makes sense in terms of what you're seeing. So some of the things that we've learned about these disks, which is quite extraordinary, is that the disks are becoming unbound because of the enormous star formation rates. So when you look at an ALMA galaxy, for example, the ALMA disk, the star formation rates are so enormous, it's circulating so much gas into the CGM above and below, and it's reaccreting as well, that the disk itself is becoming severely destabilized. And that is an irreversible process which will tend to thicken the disk. So gas fractions so that what I'm showing you here is the gravitational potential as a function of radius versus at t equals 0 compared to r at some later time. So a flat line means that the gravitational potential at all radii is the same as the starting point. And what you see here is the gravitational potential is weakening over cosmic time. But in the case of 20%, not much happens. 40%, the effect is more dramatic. 60%, you can see how it sort of it goes for a minimum, comes back a bit because the disk is reaccreting. And at 80%, the effect is even more dramatic. And at 100%, you see that you've lost essentially half. You've lost half the gravitational potential of the field. The field itself is weakened by at least a factor of 2, and then it tries to reaccrete in time, but never gets back to where it was before. So what you're seeing here is this disk is becoming unbound. I'm not saying it's completely unbound. It's just becoming much weaker with cosmic time, and therefore the stars tend to move upwards and outwards, which in a sense helps to loosen the disk, which also assists the heating of the disk as the stuff is sloshing around within the galaxy. So you can actually work out, does this make sense in terms of the star formation rate? And it does. The time scale it takes to lose half the mass just requires a burst of 27 solar masses per year, efficiencies of 100% coupling. It's much weaker. This is at the center. It's much weaker at sort of the solar radius, 10 kiloparsecs or so. That would be down by another factor of 30 or so. But anyway, the numbers make sense in terms of the star formation rate that we see. The unbinding of the disk is entirely consistent with that picture. So a question that James Binney asked when I showed him this was, is this the same era that destroyed the NFW cusp at the Milky Way center? Because remember that in dwarf galaxies, Ponce and Governato and people have shown that if you have this pumping mechanism of gas and star formation being pushed out from the center, the dark matter gets carried with it, and that tends to blur the NFW cusp that we assume exists because of the dark matter only simulations work for people like Matthias is famous for over the years. But assuming it ever existed, is this process enough to remove the cusp? And I think the answer is no. This is a density profile of the dark matter halo as a function of radius. And what you can't see in there is they're all overlaying each other, are the density profiles as a function of time. So if you take the first curve and divide into all the other curves, there's not much evolution over 2 billion years. At 80% gas fraction, you do actually weaken the central cusp by sort of 20, 30%. And here are all the other curves. And at 100% gas fraction, you kind of weaken the cusp by a factor of 2, but that wouldn't be enough to remove it by a sort of factor of 10 or 30 or something, which is what you need for the Milky Way. So I don't think this sort of unbinding of the disk and ALMA levels of star formation in a Milky Way potential is enough to wipe out the NFW cusp. It would have been a nice idea if the thickening of the disk was contemporaneous with the NFW cusp being wiped out, but I don't think this doesn't seem to be what's happening. I mean, we weaken the cusp if it was there, but you don't remove it completely. So there's no analogy here with dwarf galaxies. Okay, so let me just show you now to finish up. Let me just show you now what's going on in terms of the process. So remember how I showed you this Brownian motion plot. Where's it gone? Here. There are parts of the motion which are essentially where the disk is floating, and then it undergoes these rapid reversals. It sort of undergoes some sort of change and comes back along its track. And here it's even more dramatic. So it's actually a forward in time. Because forward in time, it's drifting relatively easily, and then it's drifting again after turning a corner, comes back along its own trajectory, and again here, and then drifts like this. So what these turn points you can relate to the heating itself. So, for example, this is the z height of the disk as a function of time, and this is from 0 to 2 billion years. And you see how the heating is sort of systematic for a while. Oops, sorry, apologies. The heating is rising for a while, and then it sort of saturates for a while, for maybe a few 100 million years. Then it rises again and saturates again for a few 100 million years, and it rises again and saturates again, and so forth. So these look to be, the heating effect looks to be most dramatic at the reversals along its trajectory, at least if I've got my timing right. And so basically you can understand this sort of plot in terms of the baryon sloshing. I mean, you've got the whole disk it's not just one region of the disk which you get, say, from mergers. The whole disk is being rattled or shaken up and down, as you can see from this plot here, the R sloshing plot. You can see how it's sort of the radial sloshing going on, and how the sloshing motion plus or minus 20 kilometers per second in time as well. So you've got the whole disk itself is being rattled and being heated very efficiently, and it's not just up and down. It's happening in 3 dimensions. So the heating, to summarize, quite an extensive piece of work, I suppose, but it would take too long to go through. The heating in sigma, the dispersion relation in phi and R and Z, for example, it appears to be mostly isotropic. It manifests most clearly in Z because Z's the coldest component. That's the one that can go the furthest in terms of the heating. But sigma R and sigma phi are much larger numbers for any disk. But you do see them evolve. So for example, this is the radial scale length of that thickened disk, and you see how it rises and then essentially hits this number today, which is 2 kiloparsecs, the scale length of the thick disk today. So you do get some radial growth in the disk from this process, but the effect is most pronounced in the vertical heating because it starts from a much lower base. The vertical heating, so an isotropic heating in R, phi, and Z would still benefit the Z component most efficiently in terms of what you observe. So let me finish up the last few slides. The chemistry is difficult in the sense that we have initial chemistry, and like everybody else who does these simulations, we set ourselves up for success. When you've got star bursting, star formation, your mass function tends to be biased in the early epoch towards type 2 supernovae, and they have strong alpha enrichment. So of course the old stars tend to be alpha enriched. So at the present time, I don't think there's anything about our work which is predictive in terms of the chemistry, not at the present time. But we do get some of the general properties right, I think, in terms of what we know about the thick disk today. So, for example, this is from Cherqui, Misha Hayward, and Paolo Di Matteo in Paris. They've got this observation from Gaia of the age metallicity relationship in the thick disk component. So it rises to in metallicity, and then we sort of see a general trend like that. There's an age metallicity dependence in the thickened disk component. Also, if you look at the metallicity and age, this is the age diagram. Stars are older further off the plane as a consequence of this process. The gradient is stronger vertically than in radius, which we think is consistent with observation. The same thing is true in metallicity. The metallicity shows a stronger gradient vertically than it does in radius, again, which I think is consistent with observation. So I don't put much stock in the chemistry stuff at the present time because I don't think anyone really gets the chemistry right in terms of sort of predictive properties. But we set ourselves up for success, I suppose, by having powerful star formation producing alpha-enriched stars. So let me just finish up now. So does in situ star formation in a turbulent medium lead to thick stellar disks? You'll certainly find this claim in a lot of papers, especially in cosmological papers where the resolution is much lower. And does this explain the Milky Way's old thick disk? I think the answer is no. At least in our work, I would say that the answer is no. Turbulent thick disks don't generate thick stellar disks. That's not what's going on. Let me show you why I think that's true. So what I'm showing you here is, this is to finish up now, I'm almost finished. The vertical scale, the vertical disk height, 0 to 3 kiloparsecs is a function of time. That's 0 billion years, 2 billion years going this way. What I'm showing you here on a linear scale is where the stars are born. And this is in color, so you can see the gradient in the structure, and this is in halftone, so you can see it as a sort of just a visual image. And what you see here is that there's stars being born at all scale heights. But the only stars that are born in equilibrium are the stars which are essentially born into the dense molecular clouds in the plane. These stars are sort of injected with random energies, random phases, and don't necessarily hang around at those scale heights. And I'll show you that this is borne out with the kinematics in a moment. So this is 20%, this is 40%, this is 60%, this is 80%, this is 100%. You see it's very choppy. This is because of the episodic nature of the star formation. And what I'm showing you here is where the newly formed stars are being born as a function of height and in time. And we would argue that these are all pretty much the same. 20%, 40%, 60, 80, and 100% gas fraction. The source function of where the stars are born looks the same in all these figures. And in terms of grayscale, the same is true as well. You see pretty much the same distribution of where the stars are being born. Okay, but when you look at it in terms of where the heating is going on, these are a strong function of the gas fraction. 20%, 40%, 60%, 80%, and 100%. And that black cross is showing you the scale height of the thick disk at the sun's radius, the solar circle. So you see my point now, that regardless of the source function, the vertical heating, even if the source function is the same in all cases, the heating is very different as a function of the gas fraction. And as far as we can determine, the only thing that explains this is in fact the sloshing of the baryons within the dark matter halo potential. Because you can even see it sort of in terms of those ridge lines I was showing you before. So I think what this tells us, at least, is if you are in the reference frame of this galaxy which is moving around, in that reference frame, the vertical heating is a consequence of the sloshing and the changing potential with respect to the underlying dark matter halo potential. It's not a consequence of stars forming in situ in a turbulent disk. So here's my summary. I think I have one more slide to follow this. Sloshing the disk heats it at all times due to the gravitational perturbations, but the largest contributions are from the rapid reversals. It may be the primary mechanism behind widespread occurrence of old, chemically distinct thickened disks, certainly if you think of it in terms of early disks having gone through a gas-rich phase. In our way of thinking, minor mergers are not as important. When you have a disk which is dominated by gas, it's the gas that's telling the stars what to do. So minor mergers coming in have much less of an effect and are highly localized in terms of what they can do for you. So I actually think that the gas-rich disks are determined by gas dynamics, not even by minor mergers. Of course, a major merger could have a very destructive effect, but that's a very different process altogether. And we think the Milky Way had maybe one of those in the distant past. So due to disks being thin and cold, sloshing has much more impact on the vertical profile. I've made that point already. The alpha enrichment is really a consequence of having a gas-rich phase and a mass function tipped towards the high mass stars. That's essentially almost a home run, if you will. Now, one more slide to show you is, obviously, if you're having a model and you're making these claims, there must be something predictive here that we can go after. Do we predict anything that we can search for? And the answer is yes. One thing which is really particularly interesting about these sloshing galaxies is that they are trying to solve two things. You've got the gases moving within its own potential, and also with respect to a potential which is shifting around in a potential and trying to solve the problem of being centered on the dark halo or the total potential and its own potential. And what that does is essentially shift. You've got motions which are shifting and trying to rotate with respect to the main potential, the dominant the total potential. And what that does for you is generate spiral features where they're positive on both sides. This is not what you get with spiral arms or bar streaming or tidal arms, for example. And this is a point that was made in particular by. So let me just go back a bit. So what you see with ALMA is you observe some sort of velocity field. The first thing you do is you fit a velocity field to it, subtract that velocity field, and look at the residuals. And this point was made very elegantly, I think, by Takafumi in his 2023 paper, where he showed that in this galaxy at high redshift, when he subtracts his kinematic model, he ends up with two positive residuals. And what he was expecting was a positive and a negative residual, say from tidal arms or spiral streaming or something. So one way to do this would be in terms of sloshing. If you slosh the gas and then in that sloshing frame, which is trying to rotate around two centers in a sense, and then so whatever velocity field you see, if you subtract the velocity field and find it's off-centered, also off-centered with respect to the total. I mean, the starlight doesn't have to be lined up with the gas either. I mean, that's something else that we could look for. But I think sloshing signatures, where you've got these positive residuals being preserved on both sides of the disk, may be evidence of this sort of strong dynamical effect. So my final slide is this one, and that's to say that we think we're on an interesting line of reasoning here. It's something that's worth pursuing. There's a lot to be done, and we're very happy to collaborate with people. We've already do collaborate with Gaia teams and people who have specific demands of their data. Molecular and dust summation is missing from the simulations. This is something we have a PhD student looking at right now, Dylan Theron, who's with us in Sydney from South Africa, and he's sort of looking at how to install molecules and dust into these simulations and making some good progress. The CGM is clearly important, MHD and cosmic heating. Bondi-Hoyle accretion onto black holes, because one of the things that's been pointed out to us is a lot of these ALMA galaxies have powerful quasars at the center. I don't know whether turbulent gas aids and abets or whether it suppresses and holds back. It's something I would like to think about with somebody. You know, what does turbulent gas disks do for black holes? Does it do anything at all? Massive clump formation. This point has been made by Francois Renaud and Bono, Agertz, and others. This is a very important aspect of gas-rich disks. Minor mergers and interactions. We don't know a lot about this at the moment, but when we've tried to throw things into these simulations, we don't see. It seems the gas is doing all the talking rather than the merger itself. And finally, I think one of the really interesting things, which is what we want to explore in much more detail, is what some have called galactic ecology. In other words, the evolution of stars and gas together over billions of years in terms of spiral arms and bars and resonances. And I think this is something that we need to work hard at because, of course, Gaia, LSST, and NASA Roman and future surveys will give us some very beautiful data to work with. Okay, thank you very much.
Thank you, George. Thanks for this very nice talk. So let's go for this for questions or comments. Please
I hope I made up for lost time. I apologize for the stuff that we had at the beginning.
Any questions?
Or comments or criticisms, all of the above is entirely okay.
Maybe I have one question for you. Mentioned you use the turbulence to create the thick disk and explosion disk. How do you consider the viscosity and magnetic fields and the gas softening in your simulation?
Yeah. So are you asking me what magnetic fields do to you? What they do for what happens? Yeah. So I'm very much in the hands of Christoph Federath, and I think I'm right in saying that the magnetic fields can actually suppress a lot of the cloud formation, or at least change the cloud spectrum. And so I think in principle, so for example, our coupling to the gas, where we couple radiation and momentum to the gas from the supernovae, I could imagine that story changes in the presence of cosmic ray heating into clouds, into the CGM, and also the magnetic fields maybe makes gas more compressible and you don't make the cloud mass spectrum may well be modified. So to be really honest with you, I do worry about the MHD part of it in the sense that might weaken the story somewhat.
Yeah, how about the gas softening? Your softeningness for the gas.
You're saying softening scale?
Yeah, the gas. Yeah, the softening scale for the gas in your simulation.
Yeah, you're right. So, I mean, we're down to a few parsec resolution in the best cases, and what we're doing is comparing our numbers. You know, to metrics like alpha virial and Mach numbers, and those sorts of things, and the B parameter. We're sort of comparing those in the simulation to what goes on at very high resolution. So we can't compete with a very high resolution. So to be honest with you, our clouds are not very nucleated. They're not nucleated molecular clouds. I think observations would say molecular clouds are more nucleated. So I think Christoph Federath would say that our clouds are not particularly good. They're okay, and certainly a big improvement over cosmological simulations. But they probably don't behave like real molecular clouds. So I can't say for sure that the clouds are doing the scattering. You know, Spitzer and Schwarzschild talked about molecular cloud or dense object scattering of stars, and you could argue that we don't make the clouds dense enough to get enough scattering of stars. So I think magnetic fields will higher resolution would definitely help. You know, if you went to a factor of 10 higher resolution in the gas, you probably could start to resolve the internal structure of molecular clouds.
Okay, thank you. Other questions? Bing Hui, you want to ask a question, right?
Uh, yeah, yeah.
Far
Sorry,
away.
I want to raise my hand first. Okay.
No.
Hello, this is Binghui speaking.
I can hear you, yes.
So I'm very, yes, thank you. Very nice talk. And I'm just curious about the point of the solution. So seems that your simulation is basically in somehow isolated environment, right? The gas is continuous creating.
Yes.
So will the solution also be affected by the hierarchical module during the merging history? Because I think that in the universe, many.
It's a really good question and a really good insight observation. Yes, in principle, if the accretion is drizzle, it might be difficult to if it's drizzling onto the disk. We'd have to look at the simulations much more carefully than what we've done, I suppose. If it comes in as cold clouds, I would agree with you, massive clouds. But if it comes in as like a rain or a drizzle, except if it comes in on one side, you could imagine that it makes the potential a bit lopsided. So to be honest with you, I don't think we know the answer. I think your question, your insight is really a really good one. I think this needs to be looked at more carefully. But I would expect it to be more dense, dense accretion rather than a sort of rain. It's sort of drizzly rain coming in through the hot halo. It might not be as effective at causing sloshing.
Okay, thank you.
It's such an interesting insight on your part.
Any other question?
And feel free to email us as well if you have comments or questions and or observations like that.
So now in your simulation, you only need to construct a mechanistic I noticed you only the constructor or you only care about the mechanistic and age relations. How do you consider about the other chemical abundance, such like the mechanism or others? You also mentioned the supernova too.
Yeah.
Yeah.
I would say that the chemistry needs to be improved. Oscar Gertz's work in particular, you know, he set up his paper, Wintergarten, did the chemistry probably better, and it was more properly reasoned in terms of the CDM hierarchy. And he's able to get a bimodal distribution alpha to ion. You know, he sees enhanced alpha to ion versus alpha poor. We don't yet track the simulation long enough to start building up an alpha-rich, alpha-poor bimodality. So I think chemistry is something we need. We do plan. So I'm off to Sweden in 2 weeks, basically, to work with Oscar in Lund on just this point. Like Oscar, Torsten, and I. Torsten identified chemistry as something which we need to be more convergent with the Wintergarten simulations and how the metals get put in. But we're only doing a few billion years, whereas what Oscar's doing is tracking it over 13 billion years. And he's able to build up this bimodal alpha to ion distribution. But again, if you look at the work published so far, there are very few modeling teams that get alpha to ion bimodality. Tobias Book finds it's a subset of his simulations where he sees alpha to ion bimodality. He does a good job too. But again, you know, if the Gecko's survey says it always happens, you always get alpha to ion bimodality. If that is the conclusion for 35 galaxies, then it needs to be a generic consequence of these disk evolution. But there are very few simulations that get true, clear, clean bimodality in alpha to ion. So that's something we do want to pay a lot of attention to that, more attention to the chemistry than we have so far.
See, Yeah. Any other questions? Karina, I think you want to ask something, right?
There's Grazina. Hello, Grazina.
So thank you very much. You are doing indeed very important work and investigations. You mentioned several possibilities or hypotheses for the thick disk formation. Which of those hypotheses is your favorite?
Yeah, so to be honest with you, none of them really, because I'm not sure mergers do much for you. Maybe they do. Maybe a gas-rich merger does something, but a gas-poor merger, I don't think does much for you. Um, it's a really good question. I'm not sure I know the answer at the present time. It's true. What people would normally say is to be really careful. Maybe they're all true. They all have they all contribute something. But the full narrative from starting off to going forwards matters a lot. I mean, I don't know if any of the cosmological simulations or observations have told us which one is a Milky Way progenitor. Um, to be honest with you, to be straight with you, one of the really interesting observations is that the galaxy had an early merger. This Gaia sausage Enceladus thing, or maybe it's Kraken. I don't know which one is winning out, but one of these things seems to be an early merger with the Milky Way when the Milky Way was much less massive. So of course this object was much less massive as well, but it was an important merger at that time. So simulations which try to track the Gaia sausage Enceladus accretion onto the Milky Way, if it was gas rich, could have contributed something important in terms of an early thickened old alpha-rich disk is possible. But as I say, that's just another approach. But I would say somewhere between that approach, like an early merger, and our approach, I would say is the answer. Maybe it's very difficult to know for sure what the story of the Milky Way was. I think we've all got our work cut out for years to come.
So investigations of other galaxies are also very important for this, and I'm glad you are working on that also. So thank you very much.
Gracina, that's a really interesting statement. And by the way, I know your paper with Padgel very well, Talphisian and Padgel, going years ago. I remember that paper. Your paper, you remember? About chemistry. Okay, so if, for example, let's pretend, for example, that Geckos shows that all those disks, all 35 disks, have this bimodal alpha to iron, thick alpha to iron, alpha rich, thin alpha poor, bimodality. Let's pretend that was in 5 years' time. That's the conclusion. In that case, I would not believe that an early merger is doing this, because that early merger is only seen in 1 in 10 or 1 in 30 simulations. Those that went looking for things that give you a Gaia sausage, Enceladus, they found, I think it was 1 in 30 simulations give you the conditions which give rise to Gaia sausage, coming in with the right mass at the right time, possibly even prograde, not too hyperbolic. I can't remember what they did, how they found it. So that's a relatively unusual situation. So that cannot be the generic explanation for all the Geckos bimodality observations. So therefore, what are you left with? Well, what you're left with is the idea that all disks went through a gas-rich phase, and that gas-rich phase is what caused this, because that's what they all have in common. Does that make sense? So
Actually, I think that one merge with the Gaia and Enceladus would be too small impact to my understanding to the formation of the thick disk to both directions from the thin disk, how to say, to both directions in that. And there are other merging streams, many streams.
yeah,
The importance maybe was larger for the halo of such mergers.
yeah,
So indeed, there is a lot of investigations remain.
yeah. But I would just say, if Geckos reveals that everybody has alpha bimodality, if that's the conclusion, and we don't know yet, it's much too soon. I've been hearing their update meeting talks, and you can clearly see they're working so hard to get their chemistry right. It's not easy to do faint star alpha to ion measurements. But if that's the conclusion, I would say it's something intrinsic to the early disk that's doing it, because you cannot arrange for all of them to have this 3-to-1 ratio merger happening at a redshift of 2 to 5 to give you the Gaia sausage kind of behavior. I would find that really unlikely. Then I would say it's a gas phase effect. It's to do with gas accretion and turbulence and that's driving this, and the gas rattling the galaxy around and so forth. I would say that would be one process that would be common to all the gas-rich disks. Okay, so anyway, well, I'm getting ahead of myself. We don't know what the answer is yet.
Okay, it is good for us. We will have a job.
Do what? Yeah.
So it is good that there are unanswered questions.
Yeah.
Always for scientists will be some job
Yeah.
to do.
Absolutely. We never prove anything in astronomy. We just abandon models and move on. We never prove anything. So we'll probably be in business for the next 100 years.
Okay.
Not me. I won't be around for 100 years, but so anyway, thanks so much for your questions and insights. That's really helpful.
Any other questions? Any other questions?
And don't forget to send them by email if that helps.
Yeah, Ray, you want to ask us something? I noticed you open your video or not.
No, thanks.
Hello, Rui.
Yeah. Yeah. I have a small question. So, if you think that high gas rate disk will result in the thick disk, so maybe I mean the fraction of gas rate disk will be small, and then it will result in the thick disk fraction at high redshift. So, can your model predict the fraction of thick disk at high Z and compare with the observation?
Yeah, great question. Again, you're asking the absolutely right questions that we don't have enough answers for. So one reason for going to Sweden in 2 weeks to work with Oscar is we want to put this framework within the Wintergarten framework. So he's already done a work with a colleague where you can have a controlled simulation within a cosmological simulation. Essentially, what's advected over the surface is what comes from the simulation itself. So we want the best. We want the best of both worlds: the cosmological accretion history and the ability to control the simulation, where you turn parameters on and off to see what's really going on. And so I can't answer your question until we achieve that goal. We need to sort of synthesize Nexus within the Wintergarten framework, and that's one of our missions. And we'll be talking about that in Sweden in 2 weeks' time.
Okay, thanks.
But thank you very much for the question, because that's something we'd like to answer.
Any others? Maybe I have the last one.
Okay.
Did you compare different profiles? You mentioned the FW profile, and if you adopt the Inast profile or the water valence profile, how is
I agree.
affect your results? Yeah.
Same question was asked by Glenn van der Ven in Austria. He asked the same question as you did. And to be honest with you, we haven't, to be straight with you, we haven't really looked at the dark matter probe halos. I mean, I don't even think we've looked at halo rotation, have we, Torsten? There's a modest amount of rotation in the light halos.
No net rotation. No,
Okay.
no.
It's in your paper that the prospect of doing that is there.
Because again, if I may just add to that, so we're trying to have the simplest models possible before we go on to add more complexities, and that's the reason.
Yeah.
So getting rid of any parameters that might obfuscate, the physics we're actually looking at.
Your paper does talk about the effect of having consistent baryon cooling in a rotating dark matter halo. You were able to switch that on.
it's possible to put that in, but we didn't in this model series.
Yeah, so hopefully that'll be so the whole MoMA White framework where you sort of turn all these knobs on and make it all possible. You can MoMA White, basically form their disks from the cooling hot halo, and the conservation angular momentum is the spin up you get from your hot halo, and lambda halo is like 0.05 or 0.03 or something. So you conserve that, and that gives you the angular momentum. So that's what's happening now. Torsten's made good progress on installing the MoMA White framework within Nexus.
See. Okay. Any others? If no more, or maybe we see you this time.
And thank you very much indeed to everybody online. It was great to see you all. The ones who put your cameras on, I couldn't see half of your faces.
Super thanks, yours.
Yeah, thanks very much indeed. That was great. Ryu and Yuru, and Christina, thank you very much.
Yeah. Okay.
All
okay. Bye bye. Yeah.
Send you the link to the video.
Yeah. Yes.